All right, now let's look. We've considered the direct shear test. Let's look at the triaxial test. The direct shear test is really simple. The triaxial test is a little more complicated, but allows us to more carefully control the shearing and loading conditions, and it much more accurately recreates the kinds of stress you have in the field, especially along the failure surface. So this is what a triaxial testing apparatus looks like. This is a cross-section. Hopefully, again, this is a review. Hopefully you've done a triaxial test in the past. So this is a cylinder, and this bar right here is a big plexiglass cylinder. And inside this cylinder, we have a column of soil. Often this column of soil has been extruded from a sampling tube. And we put it, make it flat on the top and bottom, put it in this device. You put this loading cap on top, and then you surround the whole thing with some sort of impermeable barrier. Like a lot of times that's like a latex membrane. And then you enclose it on the bottom and the top so it's sealed off. And then you can apply a load to the top, but you can also, you fill this annular space between the sample and this plexiglass with water. And there's a pore pressure. Using a valve, you can actually control what the pore pressure is inside that, and that controls the lateral stress on the side of the soil. And then that lateral stress is actually felt all the way around because it applies, the pore water applies pressure to the top. But then through this loading piston on the top, we can apply an additional load. And so what that means is this lateral pressure is sigma 3, and then the vertical pressure is sigma 1, the sigma 3 being the minor principal stress and sigma 1 being the major principal stress. And then there's also a valve. There's a porous stone on the bottom here, and you can as you shear this or you apply pressure, any excess water can drain out this valve. And you can turn that valve on or off. If you want to simulate undrained conditions, you just turn that valve off, and then the water can't escape. And again, this other opening here in the valve allows you to control this lateral pressure. And so by controlling this valve here, you can control whether you have drained or undrained conditions. So we can control sigma 1, we can control sigma 3, and then as you apply a load, basically a shear plane develops somewhere on this soil, and it fails, and we'll talk about that. So there are two types of tests you can do. You can do a compression test and an extension test. With a compression test, you increase the load here until it fails. With an extension test, you keep a constant load through the loading piston, and then you increase this sigma, or this lateral stress in the chamber, which then becomes sigma 1, and until you basically squeeze it until it fails. And interestingly, for a slope stability application, the soils at the top of the slope are in compression, and then the soils at the bottom, the toe of the slope, there's more lateral force than vertical, and so they're more would be better simulated using an extension test. So you can simulate different things. There are also two stages in the test. There's a consolidation stage and a shearing stage. What the consolidation stage means is you can apply this lateral stress with the fluid in the chamber, and if this valve is open, any excess pore pressure that builds up from that in the soil is allowed to drain off. So that is the consolidation stage. And with an unconsolidated test, you would just shut off that valve. And then the shearing phase is when you increase either the vertical load or the horizontal load. So there are different combinations of conditions here. We can do a consolidated drain test, CD, consolidated undrained, and unconsolidated undrained. And let me go back here and explain that. Consolidated drained means when you apply this pressure in the chamber, you have this open, so you let all that excess pore pressure dissipate, and then you apply the load very slowly so that any pore pressures that are generated due to shear or due to that increased loading are also allowed to drain. With a consolidated undrained test, you have the valve open during the consolidation phase and then closed during the loading phase. And then unconsolidated undrained means the valve is always closed. It's closed when you apply the chamber pressure, and it's closed when you apply the load. Why would you do these different things? Well, it allows you to simulate different types of field conditions. So these are called CD, CU, and UU. All right, so assuming we're doing a compression test, this is a diagram of our soil sample. During the consolidation stage, we increase the fluid chamber, and it's applied all the way around, and sigma C is the consolidation pressure. And then we apply a load through the loading piston that is sometimes referred to as sigma 1 minus sigma 3, so it's the difference between sigma 1 and sigma 3, or sometimes we just call it the deviator stress, or sigma D. And then, so the total stress at failure is sigma 1, which is sigma C plus the deviator stress, and then sigma 3 at failure is just your consolidation stress. All right. And let's suppose you're doing a consolidated drain test. When you first apply the fluid pressure in the chamber, this is a plot of pore pressure versus time. The pore pressures would initially go up, but you allow drainage, so those pore pressures can then, it takes time for them to dissipate. These tests can take quite a while, depending on the soil. If you have a sandy soil or more permeable soil, those pore pressures dissipate very rapidly, but if it's a low permeability clay, it could take quite a while, hours or days, theoretically. And then once you shear it, you apply that load slow enough that those any pore pressures generated due to shear are allowed to dissipate. So a consolidated drain test, it takes a long time because you have to do the consolidation stage, and then you have to shear it very slowly. So these can take up to a week or two, theoretically. All right, so again, back to this diagram with a CD test. At the end of the consolidation phase, the du dt equals 0, meaning that we're down here on the flat part of the slope. And then throughout the test, we keep that to be 0, and then we get to our eventually. What causes it to fail is the difference between sigma 1 and sigma 3. And eventually a failure plane will form that goes on a diagonal like this. And so that's how this works. And now if you were to, let's suppose you were to plot this. So this would be the failure envelope for your CD triaxial test. Sigma C, this is your confining stress, your consolidation stress. And at the end of the consolidation stage, the sigma 1 is equal to sigma 3, so it's just a dot. But then, as you apply the deviator stress, as you slowly apply it, sigma 1, the vertical stress, becomes greater than the lateral stress, and you get a little circle will appear. And then that circle will gradually grow and grow until you intercept that failure surface. And then the failure would occur at this combination of total stress and shear stress. And this would be sigma 1 prime and sigma 3 prime. This end of the circle, this is your vertical stress, and this is your horizontal stress. And then this would be the stress on the failure plane, which is at an angle. So this is what I mentioned, this failure plane is at an angle. the angle of that is 45 plus the friction angle divided by 2. And you can solve for that if you want. That's how you find this. You can do it from Moore's circle. And now this is, if we have a normally consolidated clay or loose sand, then this line, there's no cohesion intercept. And we can calculate this friction angle. It's sigma 1 minus sigma 3 over sigma 1 plus sigma 3 at failure. So we just get these two values. This, again, this is the vertical stress. This is the lateral stress. And we can solve for phi. If you want to know what these two values are here, the normal stress at failure is equal, you can get from this equation, and the shear stress at failure you can get from this equation. Well, relative to this angle, excuse me. But once you have the what we really need from this is this friction angle, because that gives us our strength. All right, what if you have an over-consolidated clay or dense sand? Now we have a cohesion intercept. And basically you have to run this multiple times at different stresses to figure out what that intercept would be. Different confining stresses, but again, this angle, it fails, is 45 plus phi over 2. But now we have, this different relationship between sigma 1 and sigma 3. If you want to look at pore pressures versus time for a CU test, consolidated, undrained, again, the consolidation stage is the same. You apply the confining stress, the consolidation stress, and allow that to dissipate for as long as it takes, and then you close the valve and you shear it under undrained conditions. And assuming for most soils that shearing process will cause your pore pressures in the shear zone to increase, and so it would look something like this. Now the magnitude of this could change, so the pore pressures actually increase over time, although it could be negative. So this could be down here somewhere if you have a dense sand or a heavily over-consolidated clay. All right, so a CU test. We start out with our initial pore pressure. We apply the confining stress. At the end of the consolidation stage, that pore pressure is 0. And then we apply the deviator stress that causes the pore pressure to go, well, it'll go up because of the application of the deviator stress. But then, due to the shear, we don't know exactly how much that pore pressure will change. So the pore pressure is actually unknown at the end. So we don't directly know the sigma 1 prime and sigma 3 prime. So we consider this a total stress analysis. Okay, it's not whereas the CD test is an effective stress analysis, the CU test is a total stress analysis. And so if this is our Moore's circle as a point at the end of the consolidation stage, then as the circle begins to grow, if you're plotting only effective stresses, again, it would increase to failure just like before. Or excuse me, if you're plotting total stresses, it would look like this. But if there's another version of this called a CU bar test. And with a CU bar test, you have a gauge that measures the pressure coming from that tube that's attached to the drainage plate on the soil. The valve is closed, but you can measure the pressure. And so with a CU bar test, you can actually measure what that pore pressure would be during shear, and due to the application of the load, and then if you subtract that from your total stresses, you can do an effective stress analysis. And in this case, the curves get a little interesting. So if you start out right here as a dot, as you begin to apply a deviator stress, this curve shifts to the left because as the pore pressures increase, the effective stress goes down. And so the curve actually grows like this. Okay, let me replay that. So it shifts to the left and then it fails over here somewhere. Remember with the direct shear test, we had a line that kind of went up like this. It's kind of the same principle is involved here. And that then becomes sigma 1 prime and sigma 3 prime. And if you look at a CU versus a CU bar test for the same soil, if you look just at total stresses, you'd get this friction angle, but if you subtract the pore pressure, basically it shifts your Moore's circle over to the left by a magnitude of the pore pressure, and then you get this phi bar CU curve. So nice thing about a CU bar test is you can get both total stresses and effective stresses out of the same test. All right. Now, by the way, we kind of skipped over a little bit, but it's possible if you have a really stiff soil or a heavily overconsolidated clay that instead of this circle growing to the left, it could grow to the right. I don't have an animation illustrating this, but you can actually go to the right, and in that case, your if the pore pressures are negative, then the phi CU could actually be greater. The undrained strength could be greater than the drain strength or the effective stress envelope. All right, now let's jump to the UU test. Unconsolidated, undrained, and if we have unsaturated soils, so now we're not dealing with saturated soils, so you don't have the pore pressure buildup that we have. And in this case, the circles grow like this, and we get failure, and we come up with a phi UU curve. Again, you have to repeat it with different consolidation stresses to find out what the cohesion intercept is. But with saturated soils, you take your soil, you push this out of a tube, okay? You sample it down in the ground, you bring it up to the surface, you push it out of the tube, and you keep it from, you keep these samples tightly packed, airtight, and so that soil will try to expand, and the total stress is 0, but the effective stress is equal to the total stress minus its initial pore pressure, and that initial pore pressure is 0. Basically, when the soil tries to expand, it creates suction or negative pore pressure inside the soil, and that maintains a certain amount of effective stress in the soil. Then you apply your consolidation stress, but that is not allowed to drain, so whatever consolidation stress you apply is carried by the pore water and the total stress in equal amounts, so the effective stress doesn't change. It's still equal to whatever it was to begin with. And then during shearing, we don't know what the pore pressure is. We don't measure it here, and so we don't know what the effective stress is. So this is what we call a total stress analysis, an undrained analysis, and shear strength is a function of effective stress and density. The effective stress does not change here during the consolidation stage. So what happens for saturated soils, whatever confining stress you apply here, it doesn't change the effective stress because it's all carried by the pore water pressure. And as a result of that, this Moore's circle is flat. The friction angle is 0. And so, these circles represent different confining stresses, and the circle always grows to the same size before it fails. And so we sometimes, in undrained strength, sometimes we just say phi equals 0, and the undrained strength is just a measure of this CUU. We often call it S sub U, and it's basically 1/2 of the diameter of this circle. And yeah, here we go, S sub U right here. And again, this, hopefully you've seen this before. It's just a review. but that a UU test gives you the undrained strength. Now, there's a special test that's similar to a triaxial test called an unconfined compression test. And in this case, we push that sample out of the tube. We don't encase it with a membrane. We don't apply a consolidation stress. We just throw it in this device and we test it to failure. So we're counting on, remember, if that soil is saturated, when you take it out of the tube, it'll expand a little bit. But as long as you do this quickly and you don't allow those pore pressures to dissipate that initial suction caused by that expansion of the soil will hold that together, and how much it tries to expand is a function of how deep the soil was in the ground, right? And in any case, with an unconfined compression test, it grows like this and then it fails. You always start, sigma 3 is always 0, so you're always starting right over here at the origin, and it grows to the right, and then it fails, and then that the height of that circle at failure is basically the undrained strength. We sometimes report this entire difference here, sigma 1 and sigma 3, which is basically the load you apply vertically to this sample as the unconfined compressive strength. And you just have to remember that if it's reported that way, that the undrained strength, this undrained cohesion here is 1/2 of QU. And of course, the friction angle is 0. So these, if you're dealing with undrained strength, it's just a single cohesion number represents the shear strength of the soil. Now, if you were to go out and take samples at different depths, again, the deeper that soil is, when you bring it to the surface, it's been subjected to a higher stress, so it's going to try to expand more, dilate more, and that generates a higher negative stresses, which generates a higher effective stress, and ultimately you get a higher shear strength. So the undrained strength you measure will increase with depth of sample. And the slope of this line, the change in strength divided by the change in depth, this is sometimes called a C over P ratio, or delta SU over delta Y ratio. And sometimes in your slope stability software, you can input a C over P ratio. And then it just, depending on if it's looking at a point that's a certain distance below the ground surface, it'll just scale the corresponding shear strength using this diagram. All right, so drained versus undrained. How do you decide which one to do, which one to use when you're doing the slope stability analysis? Remember, strength is a function of effective stress, and effective stress is a function of both the pore pressures and loading conditions. So you kind of need to consider what happens to the effective stress over time. Is the load going to be applied very slowly? If you put a load at the top of a slope, is it going to be applied rapidly? Well, then it would be unconsolidated, right? So maybe, if it's fully saturated, you also have to consider the permeability of the soil. Saturated clays, it's very common to assume undrained conditions and just use the undrained strength SU coming from an unconfined compression test or a UU triaxial test. Another thing you have to consider is what's going to happen to the effective stresses over time. If they're going to increase over time by the transfer of the total stress or the normal stress to the effective stress because of the drainage of the soil, then the undrained conditions will be critical. If the effective stress are going to decrease over time, the long-term or drained conditions may be critical. So maybe that the loading process will cause the soil to dilate, and in that case, the drain conditions might be the lower of the two. So, man, there's a lot to think about. I'm not going to pretend this is trivial. You have to really think about it a lot, but it's one of those things that the more you do it, the more experience you'll get, and it will become more intuitive to you. In this class, I will generally be telling you whether we're doing a drained or an undrained analysis and give you the strength parameters you need. But in a real-world situation, you've got to think very carefully about this and determine what shear strength properties you need to develop for the test.